So I alluded to a lot of what you're going to see right now yesterday, but I'm excited to present this paper again with my co-author and friend Ryan Hill, Race to the Bottom, Competition and Quality in Science. So I'll probably move through the introduction. Okay. I'll probably move through the introduction pretty quickly because in some sense yesterday was like a very extended introduction. But as we talked about yesterday, basic science doesn't lead to things that are necessarily directly commercializable. And so, but at the same time, that doesn't mean that it's not super important. However, because these advances don't lead to things that are easily bought or sold, we think that credit for ideas is sort of more important in terms of being the currency of scientific careers than necessarily profits from these ideas or papers that they're going to write. And credit, we think, in science comes at least in part from being the first to disclose a finding. And so then it's not surprising that history is full of examples of priority races and fierce competition to be first. Here you see Newton and Leibniz, and then you see Charles Darwin and the sort of lesser known Alfred Wallace.
There's a correlation here, Stein.
Yeah, maybe. Okay, so this competition in science, when you think about it, there's sort of potentially a double-edged sword. So scientists are competing to publish their findings first and establish priority. This could be good because it might just increase the pace of innovation. And it also induces scientists to disclose their work because it's only by putting their work out into the public domain that they can actually get the credit for being first. And disclosure, we think, is a good thing. On the other hand, the competition in science may have a dark side. This could manifest in a variety of ways, but one way that we think is important, possibly, is that scientists might cut corners and do lower quality work if that speeds them up and allows them to publish first. So I showed you this quote yesterday. I just love it because at some point, we'll talk about the model, and the forces in the model are just like really captured very powerfully in this quote. So Svante Pääbo is an evolutionary geneticist, and he actually won the Nobel Prize, I think, 2 years ago. And he was working, a big project he was working on was trying to sequence the Neanderthal genome, and he writes about it in this book. And in this book, he talks about competing with somebody else who's working on the same project as him, someone named Hendrik. And he says this, he says, Hendrik's paper illustrated a dilemma in science. Doing all the analyses and experiments necessary to tell the complete story leaves you vulnerable to being beaten to the press. Even when you publish a better paper, you are seen as mopping up the details after someone else who made the real breakthrough. So here you can see there's sort of this tension where if you spend longer, the paper will be better quality. And scientists care about that. But also if you spend longer, it increases the probability that somebody else comes in and preempts you.
Svante was second.
That's actually a very good question. And I don't know in this case the exact answer.
Okay, I know that prize means there would be credit.
Yeah, although there's interesting cases, like another famous example, which is very related to structural biology, was the race to solve the ribosome, which is a very complicated 3D structure. And the Nobel Prize ended up being shared 3 ways by people who are on 3 different teams. And they talk a lot in that book too about the importance not only of sort of being first, but also then of hitting the road and being out there, publicizing what you did, because that's also very important in sort of the credit aspect. So that's, of course, it's very absent in this paper, but was discussed a lot in that book, which was called, I think it's called Gene Machine. It's an interesting book. Okay. So the goal of this project is to try to answer 2 related questions. First, is it in fact true that this competition to be first leads to lower quality research? And then second, if that's true, what are the implications of that from a welfare and policy perspective? And so we're going to do this by first just developing a simple model of competition and racing in science, which is going to generate some predictions. And then we're going to try to test these predictions in the field of structural biology, which is going to have some very nice data features that will let us measure things that would be quite hard to measure in other fields of science. And then at the end, think a little bit about welfare and policy implications of having this system in science where there's a premium for being first. Okay, so this is a little redundant, but what is structural biology? It's the study of the 3D structure of biological macromolecules, which basically means I want to figure out the 3D structure of a protein. One reason to study it is that it's an important field of science. So just to give you like a little bit of context, this is a clip from the journal Science. And what you're looking at here is a 3D model of the COVID-19 spike protein. So if you know, you've probably all seen images of the COVID-19 virus. It's like the sphere coated in these little spikes. These little spikes are the spike protein. And it's this spike protein that your immune system needs to learn how to recognize in order to mount its immune response. So very early in the pandemic, scientists were working really hard to figure out this 3D structure, because that was going to be a really important input into the vaccine development efforts, which are all about training your body to recognize this thing. So that's one reason to focus on it. Over a dozen Nobel Prizes have been awarded in this field. But another reason, sort of more practical reason, is just that there's really uniquely good data in the field of structural biology in the protein data bank. So these are going to include things like objective measures of a project's quality of execution, fairly detailed project timelines that'll let us know who was working on what structure when, links to the publications, and lots of other details about the project. Okay, so just to preview the results, we develop a model which predicts that proteins are projects that are ex ante important. So proteins that we sort of know something about, like the COVID-19 spike protein, where we sort of understand that this would be really useful if somebody solved it. Those projects are going to be more competitive because lots of people want to work on the science that's going to be impactful. But if those projects are going to be the most competitive, then it's also those projects we expect scientists to endogenously decide to rush on more, and therefore the projects will be lower quality. Yeah.
Just to understand like how the process works of actually arriving at quality results, is there like anything intellectually new in the process that needs to be done, or is it like mainly like how many arrays do you assign at once to work on this?
Yeah, I would say it's a bit of a mix of both. In some ways, from reading some books on it, it almost seems more like an engineering problem in a sense. Like you will sort of have some results, they're low quality, and with your methodology and keep trying new things. So there's sort of an element, I'll talk about the process of solving these structures in more detail. There's sort of a mix of trial and error and just trying more things can be very helpful. And then there's also sort of a phase of like iterating on the model building side, where you're sort of, you build a model, you check the fit, you tweak, you check the fit, and depending on how long you spend doing that. So there's sort of a mix, I think, of like troubleshooting and trying to think of some new ways to solve problems you're having, and I think a bit more of a brute force.
But it's kind of sequential, you cannot parallelize the whole thing by just more people.
There's a very sort of two-step process, but for sure there is a notion which this model is going to ignore, which is that throwing more resources at a problem would be a way of doing it quicker, potentially without sacrificing quality. And that's not going to be captured in this model. We do some sort of robustness checks, and we do see things like, for more important projects, it looks like more authors are on the paper, which would be exactly what you're suggesting. That should be a force that pushes us away from finding that these important projects are done more badly. If that was enough to sort of fully offset, what we would see is they're done quickly, but at high quality. And so I think what's going on is that this is happening to some extent, but it's not enough to sort of make up for the deficient quality. And it's something that we have thought about at various times, like, should we just make this an additional choice in the model? But it just really complicated things, and it sort of seemed like it wasn't the core thing that was really driving our results.
But formally, it sounds a little bit like a labor search model or something. It's very like a search intensity, but also a stopping time.
Yes.
To get like new offers.
Yes. I think that's it. That's a good way to think about it, perhaps. I'm trying to think, what is in these labor search models, what is the marginal benefit, marginal cost you're trading? The marginal cost you're trading off is clear.
It's like getting a better quality job or better higher wage, right?
Yeah. So I think the trade-off is actually is somewhat.
So have to decide when to stop and have to decide how much effort to invest by themselves.
Yeah. If there's time at the end, I can show you the first order conditions we have, and we can think about like how similar or different those models are.
So if the competitiveness of this project is harder, so the likelihood of being scooped is also higher.
Yeah.
Would we expect some sorting into the people that decide to enter into those programs?
That's a great question. That's also absent from our model, but something that we see in reality. So if you think about like some things that you think might sort of correlated with the lab having a lot of resources, for example, so things like the PI being at a highly ranked institution, we see sorting on that dimension. So we see that high potential structures are more likely to have principal investigators from highly ranked universities working on them. And so again, we sort of are comfortable ignoring that in the model because you would think if that sort of actually pushes the results, it pushes us away from finding what we find, because it's the people with more resources working on these high potential projects, and yet they're still lower quality. But again, that's like another force that I think is for sure operating in the background. Yeah. Okay.
Or you could have like, I don't know, maybe the better researchers are the ones more interested in original questions.
That is also true. And so maybe they don't, but I would just think that they probably do have more resources, which you would think would sort of mechanically help you do high quality work. I mean, that sort of more pernicious version of this you worry about is that there's a type of researcher who doesn't care about doing high quality work, and those people sort into the high potential projects because that's how you win. So what we can do actually, I don't think I have the slide with me today. We can replicate all of these results using PI fixed effects. You're basically looking within the lab at this PI set of projects, and actually the magnitudes are surprisingly similar. So it seems like within researcher, people are doing lower quality work on the more important projects.
So yesterday you were showing that if you were a well-established researcher, you were scooped, you were not that much less than if you were a less known
So
researcher.
here you might worry that you also might worry that a well-established researcher can just get away with lower quality in a way that somebody else could not. So again, I think these PI fixed effect results sort of help speak to concern. Yeah, I should really have them in here. Actually, one of the comments we've got is that like currently those are the appendix of a paper. Like those really need to be more front and center. So that's like the bit sort of the intuition of the model. And what we find in the data is that indeed high potential projects, I'll tell you how we define that, but for the moment, high potential projects, we can see they're more competitive in the sense that we observe multiple researchers working on these proteins at the same time. We then see that these same high potential projects are completed on a shorter time horizon, and they look like they're lower quality. Then we think a little bit about follow-on work. So you might think, you know, it's not so much of a concern if there's low quality work as long as other people come along and sort of fix it up. And we do see that happening. That helps attenuate this negative relationship between the importance of the question and its quality of execution. But it doesn't totally eliminate it. And I'll talk about we think it's very expensive. We spend a lot of money fixing up bad research that probably could have been done at a higher quality initially if these first researchers had just slowed down a little bit. And then lastly, we have some suggestive evidence that these quality effects we're talking about are large enough to matter in terms of this research being useful for people who want to build on it. We look at a very particular type of follow-on research, which is designing drugs to target these proteins. And we have some suggestive evidence that it's hard to design drugs for proteins if they have not been solved at a high quality. Okay, and actually I'll just skip this for now. So, you know, we're not the first people to think about these issues. I think actually the people, as I was talking yesterday, who really thought about a lot of these issues the most are sociologists. But there's sort of some economists who are also trying to think about incentives in science. This Dasgupta and David paper, I think, is very nice, where they call for what they call a new economics of science. Try to think about these more micro incentives that scientists face. We also build on a theoretical literature on patent and R&D racing, and I in particular want to highlight this Bodchev, Bolt, and Mariotti paper called The Researcher's Dilemma. Our model builds very much on what they're doing, really thinking about a very similar set of forces. And then sort of lastly, we were just very inspired actually by reading sort of op-eds in science journals about how what scientists feel like is going on in their field and sort of the challenges and the struggles and problems. I would say I hope what our primary contribution can be is to bring some empirics to what has largely been a theoretical discussion. to date. Okay, so let me walk through the model in just a couple of slides. So we conceptualize projects in varying in what we call their ex ante potential. So this is supposed to capture the idea that before you start a project, so if you're a structural biologist, before you start trying to figure out a protein structure, you have some understanding that if I succeed, this is either going to be like a home run and publish in Science, and it's going to be really useful, or I'm solving a protein structure for some obscure protein in a zebrafish, and I might want to do it, but it's not going to really attract that much attention. So we're just trying to capture the idea that scientists, as they sort of look across the set of projects they could be working on, they have some conception that some projects are more important than others, and there's agreement across scientists over this. Okay, whoa. Okay, so once a scientist is working on a project, they need to make a decision. They need to decide how long they're going to spend working on it. We call this borrowing the notation from that Bob Check et al. Paper. So how long are they going to let the project mature for? And when they choose this M, they trade off on the margin a marginal quality improvement, so Q of M, which is increasing in M, but with diminishing marginal returns. They trade this off against the marginal cost, which is the threat that somebody comes in that little interval of time and scoops them. And the balance of that trade-off is going to dictate when the scientist says, okay, enough, this is good enough. It's no longer worth spending a little bit more time because the risk is too high of getting scooped. That's really that Svante Pavlov quote, this line right here. The key ingredient, though, to our model, which makes it, I think, a little bit different, is that we think about project entry as being endogenous. Scientists get to choose which projects they work on. And what that means in this setup is that there's more likely to be multiple people entering, i.e. competition, when the project is a high potential. The way we operationalize this here, which lines up a little bit with the way that structural biology actually works, is we say that in order to start a project, you need to make some big investment. So you could think about this as like you need to spend time writing a grant. In structural biology, we think about it as more like you need to try to grow the crystal. The more you invest in trying to start it up, the higher is the likelihood you succeed. And so you can think that in high potential projects, everyone's willing to invest more in trying to start the project. So it's more likely that multiple people enter. So it's more likely you're engaged in a competition. So the key result when you put these pieces together is that high potential projects will be executed with lower quality. Okay. Now, one thing, I realize I deleted this slide. One thing that's important in the sort of, I don't want to get too bogged down in the details of the model, but it's important to think about what do these different competitors know about each other. And so we model this is sort of based on discussions we had with structural biologists. Structural biologists don't know for certain whether someone else is working on a project, but they have in equilibrium, they have correct beliefs about the probability that somebody else is working on the project at the same time as them. And if people want, I'm trying to see if I can.
Question link to the
Yes.
about the model. Is there a sense of a social benchmark in this model? What would be the right level of quality?
The right level of quality, yes. So that you can yes, that you can figure out by just solving the problem. So there's a couple ways you can get to the social optimum, the social planner's preferred level of maturation. One is you can just solve the problem naively, ignoring the threat of competition. And then basically what you end up equating is the marginal benefit of the quality improvement with just like the discount factor. So that's like one way you can do that. You can also like it kind of falls out in multiple ways. Another way you can do it is you solve the problem, just say that the rewards for being first and second same. You can also recover that same benchmark. But basically, the social planner wishes that the social planner doesn't care who finishes first or second. So they just wish the scientist would make this decision without worrying about being scooped. Is that make sense? Yeah.
I was comparing a bit to the model by Oppenheimer's Stein, where
Yes.
there seems to be too much entry in the
too much.
Bigger corner.
Yes, yes, so we are not gonna take a stand on that, that's a different distortion about our people over bunching on high potential projects or people sort of optimally spread out or not. And that's something I think is just a little bit beyond the scope of us to try to answer in this paper. It's like a really hard and important question, and I don't feel like the data we have gives us much leverage on it, it's something we thought a lot about. There's one thing I do with these researchers, I'll flag later, like one place we think might have a little leverage on this, but I think at the end of the day, it's best for us to not make claims if I don't answer it well.
But is there much of a social benefit at all for more than one team to work on the same protein?
So ex post, no. Ex post, if two people solve the same protein, you wish the second person hadn't because it's waste. But the way that we model this, there's some uncertainty in whether you succeed. So ex ante, you will tolerate, there's some optimal amount of duplication, because of course you want to trade off the sort of ex ante waste against the risk that nobody succeeds. So there is a notion of sort of optimal congestion, at least ex ante, when you don't know who's going to succeed.
Why not do it sequentially then? One team fails, the next one tries.
Yeah, you could do that. I mean, that requires pretty heavy-handed.
I mean, conceptually it's a.
And actually, at the very, very end, there's sort of an interesting historical fact about the way that this field used to operate and norms around people when one team saw that someone else was ahead, they bowed out, which is sort of very much the spirit. So if there's time at the end, I can talk about that. Yeah.
Isn't it a good thing to do it sort of quick and dirty if there are a lot of other people doing it, because it saves all of that wasted effort.
So I'll talk about this. You might, if it's sort of easy to build on the quick and dirty work, then yes. We think this is an example where. But
the cost of continuing is partly your cost, but social it's the cost of the other capacity.
So I think part of the way we model it is that everyone is committing ahead of time to their quality. So you're first, the person who's second is not necessarily going to do a better job. And that lines up a little bit with how some of the process works, where once you've decided that you have crystal that's good enough, that really puts an upper bound on whether you can improve the project at all. So what ends up happening is if someone does a low quality structure and someone else wants to improve upon it, that second person has to go all the way back to the beginning. And so in that case, this low quality work we think is costly because you just wish the first team had slowed down in the early phases. Not all science is like that. And actually I can talk a little bit about that, sort of whether you think that that's the right model of how science progresses would have big implications for how you feel about a system like this. And so I can talk about that when we get to the welfare section. Okay, so this leaves us with 3 predictions, which I feel like I've already said, but the first prediction is just that high potential projects generate more investments and should be more competitive. The second is that high potential projects should be completed faster and competitive projects should be completed faster and of lower quality. So if you put these two together, you get what we sort of see as the central prediction, which is that important high potential projects are finished faster and with lower quality. And so these are the predictions that we're going to try to take to the data. So now I've told you a bit about structural biology, but let me tell you a little bit more about the data we have and try to map between things we can measure in this very nice data to sort of parameters and variables in the model. So I told you a lot about structural biology and trying to figure out these 3D shapes. So how do scientists solve protein structures? So at least prior to 2018, about 90% of structures were solved using a technique called X-ray crystallography, which broadly involves 3 steps. When you start the project, you need to purify and crystallize the protein. So if you've ever grown like a salt or a sugar crystal in your kitchen, you have a pretty good idea of what you're trying to do here. You create a super saturated solution of protein. You slowly evaporate out the water and you hope that the proteins come together in this nice lattice structure. Now, in practice, this is just something that's very hard to do. There's hundreds of different experimental conditions that you could try tweaking, things like the temperature, the pH, other things you put in the solution. And to this day, this remains an extremely trial and error process. There's been sort of like machine learning efforts to try to predict what are the right conditions for different proteins, but often anecdotally, a single amino acid change can make something that beautifully crystallized just completely not amenable. So you can think of this to some extent as like the investment part of the project. You just have to try a lot of different things. It's not quite that clean because also there's sort of a part here where you might think trying more things can also raise the quality. Because you have the choice to take the first crystal you get, or you can say, I think I can do better, and you can keep trying more and more things.
It sounds like the kind of stuff great spatial optimization tries to solve, where you have like 40 different tuning parameters and you try to find them.
Oh,
And machine learning, a ton of
okay.
settings are like that.
I know there was like a big study done because people in the protein data bank are supposed to put sort of the list of conditions that they used. And my sense was that study was a pretty big failure. They could not sort of find anything that was predictive at the protein level of like how you should set up your, but that doesn't mean.
But like even within study, right? Like just you try one thing, then you try the next condition, there's all these question
Oh,
ones.
I see, sort of, yeah. My sense from talking to people is actually the biggest innovation they've had here is just robots. So that they can have a robot that can like, you know, set up literally 100 different things all at one time. So they can just do it faster and more precisely.
The key that they don't report all the things they tried didn't work.
No, and actually they're supposed to report the experimental conditions that did work, but they often don't do a very good job of that. They're incomplete. People sometimes suspect they're wrong on purpose to like be a red herring for other people. So I don't know how good that data is. I think partly because it can't be verified, so it's hard for them to enforce. Once they then have their protein crystal, they take it to a synchrotron facility. I think I'm gonna do one here, I'm not sure. And they beam it with X-rays. And that produces something called the diffraction pattern. So this little square with the black spots. So that's like your experimental data. And now what the researchers try to do is they try to reverse engineer, okay, if this is the experimental data, what must the 3D structure of the protein have been that would create data that looks like this?
It's like an X-ray laser.
It's an X-ray beam. It's, you know, like one of these like large, like circular facilities. They put it in a little tiny, you know, stand and it gets hit by the rays and then they scatter. And so this is another area where spending more time means that you can get a better and better model. So you'll start with some rough model and you'll say, okay, if this was really the model, the diffraction data would look like A. But my experimental data looks like A prime and they won't match. So you'll go back and you'll tweak your proposed model and repeat this process over and over again. This process is called refinement. You know, structural biologists will say this is sort of an art, sort of a science. There's computer software that helps, but a human touch is needed.
That's your data collection, or that's just like fitting the data?
It's just fitting the data. It's like it's just like trying to build basically a predictive model. It's a lot of Fourier transforms, is my understanding. And luck here seems to play a role. So now the protein data, what's the protein data bank? This is our data source. It was established in the early 1970s, back when there were about a dozen of these protein structures. And starting in the 1990s, at the urging of the protein data bank, the vast majority of scientific journals and most large federal funding agencies actually require scientists to submit their data to the protein data bank. So at least in the academic world, we think this is a very complete census of the proteins that have been solved. Today, actually, this slide is a little outdated. When we pulled the data in 2018, there was around 140,000 structures. Today, there's over 200,000. And so I showed you this slide yesterday, but this is just what the website looks like if you go to a proteins page. One thing I didn't flag yesterday that I'll flag today is here actually they're showing you all of the quality measures of the, and I'll talk about more about those on the next slide. Okay, so the most important thing I think that we're able to measure in this data that we really just can't do elsewhere is measuring the structure's quality. And actually we have three different sort of pretty unrelated in some ways measures that we're able to use. So the first is something called refinement resolution, which you can really think of as being very similar to the resolution of the graph. So this is actually the same protein, just as you move this way to the right, it's been solved at higher and higher levels of resolution. So you just get to see much more detail. It's a higher resolution structure. This is mostly dictated actually by the quality of the protein crystal. So if you have a high quality crystal, you're able to get higher resolution. The next measure is something called R-free, which is basically an assessment of model fit. Now, one thing that's interesting is that basically the protein data bank figured out that people were really overfitting their models. And so they actually make you hold out a sample, a subsample of your experimental data, and you assess the model fit on that holdout sample.
How can it cost that?
So they, there's all this standardized software that you have to use. And then you have to, I don't know the like sort of implementation details of this, but my sense is that through this standardized software and then this standardized scoring system that they make everyone run their results through when they upload, they are able to. But you know, I can't say that with 100% certainty. But when I sort of read papers about these measures that they've developed, they seem to be very confident that they are sort of independently validated by the protein data bank. It's not a scientist work for it.
Model fit is like correctly predicting the correction pattern.
Yes, exactly. I think it's like actually the placement of each amino acid. Yeah.
Is the R-free easier or harder based on the requirement resolution?
Based on, sorry, what?
All of the requirement resolution.
Yes, it's, yes, so if you have better refinement resolution, it's easier to get a better R-free. And it's easier to get a better, the last thing we measure are something called Ramachandran outliers. So basically there's certain chemicals that only should be able to bind at certain angles, like we just know this from chemistry. And so they will go through your proposed model bond by bond and flag instances of chemically infeasible bonds and report those as a share of the total number of bonds in your structure. So you might have 5% outliers, it would be better than having 20% outliers. Yeah.
At the NDC, you can find them.
Yes.
Do you do them separately? Because it
We
seems
do.
like they're measuring quite different.
We do them separately, and in the paper, we had them all separately, and then one of our referees was like, this is so overwhelming, put them in the appendix, but they.
The first one seems like more society, right? The data underlying it is much better. Then people can reuse that data, and it's expensive to collect the data. If your model
I
is
see.
so good, then it's not so.
You're saying that if the resolution is very good, and then this is quite poor, somebody could, without starting from scratch, take your data. And actually, it's interesting, the protein data bank, I believe, will flag when that happens. So if there's a new deposit, a new structure put in the protein data bank, but it comes from just reanalyzing someone else's data, that's flagged and it's extremely rare. I have to double check on this. I think part of it is that actually it's so computationally enormous to have the raw version of the data that the protein data bank doesn't host it. So this is not the raw data. And so I don't actually know that somebody else could pick up. So there, anyway,
They just have the model.
they just have the model, and I think largely it's because they don't have the storage space. There are alternative optional data sets where people can upload their extremely raw data, which would make it easy for someone else to try to rebuild the structure. But my sense is that it's very rare that people do that. So
It's not like a two-part problem where first you collect data and then you analyze data.
So it is a two-part problem. First, you collect the data and then you analyze it, but the protein data bank does not enforce that you put the raw data you analyzed in there. And I think their explanation is just like, we can't. And I don't know if this is sort of out of date and now they would be able to do it and they should be, but the time that it was started, it would be too hard. Another thing that we do because as we've sort of been discussing, the refinement resolution sort of constrains how good the quality of these can be. You can run some of these regressions where you use, like, for example, R3 as the dependent variable, controlling for the refinement resolution. And you still have the right sign, but this is sort of a channel, I think, so it's not really the right regression to run. This is sort of a form of bad control. So
Deviation regression.
yeah, so you could think about it that way. So there is an effect even when you control for this, but this explains a large share of it. So I interpret this as a good share of the corner cutting comes from people basically taking the first crystal rather than trying to get a really high quality one. So that's like a big portion of the effect. on top of that, then also people don't build as good. But I think if you want to sort of think like what's the total effect, you would want to combine both of those.
So for the outliers, is it feasible to impose these constraints in your estimation of the book?
You could, but then I think it's very hard to get the model to perform well on other measures that you care about. So if you're, if it's perfect, everything should work. You should have a low R free, you should have no outliers, but I think sometimes it's like a bit of a trade-off. But yeah, people have access, people can know these measures before they submit to the protein data bank. So it's not as if they upload and they're surprised. So you might worry that people sort of excessively target these measures. How much you worry about that, I think depends on like, do you think these measures are really actually capturing what we care about? Because if this is just literally what we care about, then we're completely happy if people are targeting these things. Okay, the next thing that we're able to observe here, which is somewhat unique, is we can see to some extent the amount of time scientists spent working on the project. Now, it's not perfect. We don't know when they start growing these protein crystals, which anecdotally, that's actually quite a long part of the process. But that said, once they have the protein and they go to the synchrotron, that date is marked in the protein data bank the vast majority of the time. So we know when they got their experimental data. And then moreover, we know when they deposit it into the protein data bank, which we think that happens around the time they're submitting the article to a journal. So this time in between is when they're trying to solve the protein structure, write up the draft, et cetera. And on average, this takes just over 1.5 years. Okay. The next thing we'd like to measure is how,
Just how easy is it for them to like predict how good the crystal is?
I think that you have a pretty good sense before you go to the synchrotron, because you can kind of see how orderly. So that someone was asking like, where is their creativity involved? This is the part of the process where I think people get very creative. So like, for example, sometimes you have this crystal that's like, you have a protein that's like very big and you're really struggling. And like one thing people have learned is sometimes you can embed like a heavy metal atom in the middle of the protein, and that will show up super bright on the diffraction pattern. And so in doing that, at least you locate the center, and that can like help you build out from there. Other people figured out that if they cryogenically froze their crystals, they would last longer under the X-ray beam. They could hit them more times. So this is where I think there is sort of engineering creativity going on here. It's not just brute force. Okay. The next thing we would like to be able to measure is sort of how competitive are these projects. And the way we do this is we just adapt this priority race measure that we had in our other paper, which lets us just create an indicator variable for, was this protein subject to a priority race? Were there multiple people working on it at the same time per this definition? Or does it look like only one person was working on it? Now, this is going to be, I want to flag noisy, because what we care about is from the perspective of the scientists, did they perceive this as a competitive race? That's not the same as ex post to turn out there really was a race. Those things will be correlated, but this is a noisy measure of that sort of perception of how competitive the race was.
So you would expect attenuation bias.
If we put this, yes, if we put this on the right-hand side of the progression, which is, so we avoid doing that, we try to instrument, right?
So if I'm scooped, why can't I just point to the PDB and say, look, I actually submitted this first?
So I think we have some sense of the answer to that from our other work on like, what is the penalty for being scooped and how does it arise? And our sense is, so if you look at, in this other paper, we estimate the effect of being scooped, and we show that the effect totally disappears if you control for the journal that publishes the paper. So what I think happens here is that it is not that a potential citing author pulls up both papers and says, oh, this one was published first, and then looks at the PDB and then says, oh, but it was actually deposited second. Like that's not how it works. What happens is just that millions of articles are published a year. Journals care a lot about novelty. So the one that sort of comes out first, regardless of whether it was deposited first or second, is just more likely to publish well. And then people are just more likely to run into the one that is published better.
So I thought it would be likely for two people to submits to the same high-ranked journal, right? And then the journal would go and look at the database for it.
So I talked about this yesterday, I don't know if you were here or not, but everything is hidden from the public prior to publication. So the journals they don't know. They get a manuscript for a protein. Perhaps somebody else is also working on that, has also already deposited it in the protein data bank, but both of those proteins are not going to be visible yet on the protein data bank. So there's no way for the journal to assess. So the journal just gets something, either it's, the first time they've seen it and they treat it as novel, or maybe the paper for the other one at that point has already come out, and then in which case we think it's pretty penalized. We do see some instances of 2 papers about the exact same protein coming out in the same issue of the same journal. There, we think it's very likely that basically it's kind of something like you're saying. The journal gets both submissions. They realize that these people were solved the thing at the exact same time, and they say like, hey, look, nobody should be punished here. We're going to publish these at the exact same time, so that's a tie. So we see that from time to time, but it's not super frequent. But we don't know what's going on. It's possible that one reviewer who gets a paper knows that their own paper on the same thing is currently under review somewhere else, and so they reject it or they sit on it. There's a famous example in economics of this happening. Arrow and DeBrue's, the famous general equilibrium paper. Rumor has it that Lionel Mackenzie submitted that same paper, and I think DeBrue was the editor, and he sat on it until his and Arrow's paper could come out first. David Otto told me that story. So, things like that can also be happening, and we just have no way of measuring them.
Has it ever happened that they join papers?
I think that's pretty rare that they join forces. I think the closest thing we see is like these sort of joint papers that come out literally like they're literally slotted in next to each other at the same journal. So the journal's sort of like imposing a tie.
So just to get this straight, so basically it's that even if the same journal gets two very similar submissions, they don't know who put it in the PDB first.
They don't know, yeah. Okay, then the last thing that we need to be able to measure is this idea of potential. So this is not just conveniently in the protein data bank for us, and so we have to construct it. The way that we construct it is that we can use these incredibly detailed covariates at the protein level. So you can think about, these are things like the organism the protein comes from, a detailed classification of what the protein does in the body. We can even see how many papers have been written about this protein prior to anyone solving the structure. So before we knew the structure of hemoglobin, people are still writing papers. Oh, this is what I think hemoglobin does. That's like a kind of, you can think of as like a measure of sort of the demand for the structure. We can use all of these things to try to predict how many citations we think the structure paper is going to get. And then we use this predicted citation value as the measure of potential. In some sense, what we're trying to do is like recreate the scientist's own thought process. These are all things the scientist knows about the protein before they start working on the project, and they're trying to make an assessment of how sort of successful of a paper they think it's going to generate. So we use lasso just because we have a huge number of covariates, this is a bin scatter, so not to say that we can predict this well, just that the fit is sort of good throughout the distribution, and we're able to explain about 20% of the variation in citations, realized citations, using these ex-ante characteristics of the protein. So these predicted values will be what we call potential. Okay, so now this gives us actually all the pieces to start looking at some results. So the first proposition or prediction that we had is that these high potential projects ought to be more competitive in the sense that they should be more likely to be involved in a priority race. And that's exactly what we see here. So here's the regression specification on the bottom. Actually, this is a typo. This should be just an indicator for priority race. And so what you see is that these high potential structures are more likely to be involved in priority race. And just to like avoid reading off regression coefficients, which are not so meaningful, what I'll do is just say, let's compare a protein that falls in the 90th percentile of this potential distribution that we compute to one that falls in the 10th percentile. So just think we're comparing a low potential and a high potential protein. if you take that difference, we see that high potential proteins are about 5 percentage points more likely to be in a priority race. Which sort of given the mean here is a pretty large effect. It's about a 50% increase over the low potential structures. So we see that they are much more likely to be involved in priority race. And so then does this induce people to work faster? We find that, yes, it does. So here the y-axis is now in years. And if you do this 90-10 comparison, you see that these high potential structures are completed. I feel like this is.
I was kind of thinking non-linear.
Yeah. But I also feel like this is not quite the graph I had in mind. I was just rejiggering these slides last night.
Almost looks like it has a kink.
Yeah, that's true, but this is not I think I'm showing you. I think this is actually the wrong figure. So anyway, let me not dwell on this too much, but it should be, this is not quite the right figure, I'm sorry. But high potential projects are completed faster, and as a result, they are lower quality. And so, again, looking at this 90-10 comparison, we find that high potential structures are about 0.6 standard deviations lower in quality using our quality index. If you look at each of these quality measures individually, actually the results are quite similar across all three of them. Okay, so this is sort of a cross-sectional result. And so one thing that you should be concerned about is just that these high potential projects are just different in some other way that makes them lower quality. And in particular, I think the version of omitted variables bias we were very worried about here is that high potential projects could just be more complicated. And that would be a reason why they're lower quality. That has nothing to do with our model about people racing. It's just that they're harder to solve. So that was something that we took very seriously. And I have sort of 3 pieces of evidence I can show you that I think suggest that can explain the full effect that we're seeing. Yeah.
If I'm it's a bit like that model. So what's the optimal time to cut a tree down?
Mm-hmm.
It's growing, and the growth rates, part of the opportunity cost is you want to plant a tree in the ground. Yes. And if you're a high quality project guy, value of getting another tree in the ground is sort of high. So
yes. So I think the best thing, I think, let me show you, so you're not so much worried about this.
I've only had one idea in my life. I've been working on
so I might as well just really crude intend.
So I'll just carry on.
Yeah, I understand what you're saying. So let me, I think the best, I'm going to show you 3 pieces of evidence that are sort of designed to push back against this complexity argument. But I actually think the last one is a pretty direct test of the model that might help with that concern. So if you are concerned about complexity, one thing you might try to do is just control for it. So we talked to structural biologists. I think one thing that helps us here is actually, it's just very hard to predict which projects are going to be hard. This comes back to, it's very hard to know how to crystallize a protein and which proteins will crystallize well and which will crystallize easily. So the fact that structural biologists don't even know which projects are going to be hard is comforting to us because it suggests it's just not correlated with observable things. That being said, big proteins are hard. Those tend to be harder to crystallize on average. And then once you've crystallized them, you're stuck now trying to build a bigger model, and that's harder. So what we just try to do here is control for various measures of the protein size. And so what I'm showing you here now are regressions of potential and quality. I'm showing you actually all 3 of our quality measures plus the index. And in the first panel, we don't have these complexity controls, and in the second panel, we do. So the first thing that you can see is that the R squared increases meaningfully when we add these complexity controls. So they do seem to be very predictive of the structure's ultimate quality, but the coefficient on potential remains actually quite stable. So it seems like complexity is predictive of quality. It's just not that correlated with the structure's potential. So said differently, there are small proteins that are really important. So that was, we thought, comforting. I don't think it's airtight, but it's comforting. The next thing
Could I actually just ask another question in the science? I know it's
Yeah.
a distraction with you. Because my understanding was like that the 3D structure, it's really an energy minimization problem of how like everything folds here. And so I was wondering, I guess, like if you have like a low resolution structure from the empirics, why can't you then take that as a starting point for numerical optimization to then get the high resolution, like global optimization? I mean, it's hard to do from scratch numerically just because it's so high dimensional. But once you have a fairly good idea, why not refine it numerically?
I don't
You might
know
not be
exactly the answer. I know that something to do with, they go from something called an electron density to like the actual map. And so
Sorry.
no, I don't really know the answer. I don't want to pretend that I do. But these I think are called electron densities. And then from there, they're trying to place the individual amino acids. And so if you just have these clouds, I think it's just, you have so much freedom over like where you could try to place the different amino acids. But I honestly, I don't, this is the part of the process that I understand the least well. So I think it's best to just be honest and admit I don't totally know. Okay. The next thing we do is we try to take advantage of the fact that different authors in our sample, we think, face different sets of incentives. So most of the researchers depositing in the protein data bank work at universities. Their career is defined by credit, and we think that they're going to be good. But about 20% of the structures in our sample we noticed were deposited by people who are affiliated with these things called structural genomics consortia. And these consortia are publicly funded research groups. Their mission is to sort of solve as many protein structures as they can and promptly place them into the public domain. It was sort of meant to replicate the success of the Human Genome Project. What's interesting about these researchers is that they are less focused on publishing in priority. In fact, only 20% of the structures that they deposit have an associated publication, whereas for the other researchers, over 90% of the structures they deposit have an associated publication. So these people, they're not even trying to publish. So we think that for them, being first is just not so important. So you can imagine using them as sort of a control group who has less of this competition incentive and contrast their behavior to the behavior of the university researchers. Yeah.
How does the incentive structures for this kind of researchers change compared to the academia? So are they promoted based on publications?
Yeah, so it's a very interesting question. My sense is that they work in these large internal labs. Promotion decisions are made internally. And as a result, you can kind of monitor the inputs. You can see who's exerting a lot of effort. Whereas if you think about like university researchers, they're being promoted by their dean, who doesn't know what's going on in the lab. All they see is the outputs. So that's sort of my sense. And so they kind of, but I think it's hard for these people to necessarily move into academia because they don't have that same track record, but they can be promoted internally within their own institution. Yeah.
Are you concerned about some selection?
Yeah, so just that the people who don't like competition selected to those.
Yeah, or maybe less successful people may opt out from academia.
I'll show you in a bit. It doesn't look like they're not as good at solving protein structures. If anything, it actually looks like they're better. And I think part of that is if you think about how a lab works, it's a constant funneling in and out of students who have to learn how to do this. And then by the time they're really good at it, they leave and there's new people. Whereas in these labs, you actually have people who are there for their careers. And so they actually seem like they're more efficient and potentially better. More what I worry about, and this will be actually, we try to make it very obvious in the figures, I worry that they're working on different types of proteins. So these people are in particular, they're tasked with working on proteins that are very different from proteins that anyone else has worked on. They're trying to sort of fill out the protein folding space. But as a result, they actually tend to work on disproportionately lower potential structures because there's a reason no one's working in that space. So that's actually more the concern. We had
But in a way, like all the selection effects are actually part of what you care about in terms of the incentives, right? From a policy perspective. I don't just care about the moral hazard, I care about the adverse selection.
The adverse selection.
Or sorry, that's maybe a bad metaphor, but I mean, selection effects are part of what they care about as the consequences of science policy or incentive structures.
Yeah, it just means, I'll show you in a second, these graphs, we have these like difference in differences graphs. And you can just see, so we were very intentional when we made these, trying to show that the support is different. I mean, there's quite a lot of overlap, but just that, you know, there's sort of, they're not, like, you're not estimating these slopes on sort of the exact same support. That was kind of what we were worried about. And there's just something sort of inherently different about these proteins that could be driving the results. So I think, again, let me talk through these results. I think they're not perfect. I'll show you one more thing. And my view is that we have sort of these 3 different pieces of evidence. No one is airtight, but they're all like pretty uncorrelated with each other. And so we hope that together they're compelling, that competition is really the important.
You could also restrict common support here, no?
Sorry?
You could just restrict attention to common
You
support.
could, yes, you could do that. But then I just worry also that they're sort of different in ways maybe that are not being captured by this univariate measure. So this is showing you the maturation. So in blue, you see the university researchers, and they are moving more quickly on the high potential projects. And in red, you see the structural genomics researchers who are actually, if anything, taking longer on the high potential projects. Now, the most striking thing about this figure is just the huge level difference between the two. So the structural genomics researchers are just much faster on average. We think in part that has to do with their mission. So they're not typically trying to write a paper and get it published. So that the university researchers will often wait until they have a draft and they're in the editorial process. These people, as soon as they have a structure, they put it in the data bank. But they also just could be more efficient for the reasons that I was talking about. They're sort of, they're more experts. You don't have the student bumbling around in the lab taking too long. But really what I want to focus on here is just the difference in slopes. You don't see, when you have a group that seems to experience less competition, they don't move more quickly when they're working on a high potential structure. And then you can do the same thing for quality. So in blue, you have the university researchers, and in red, you have the structural genomics researchers. Now, the structural genomics researchers, the quality is lower for the high potential projects, but it's just not nearly as steep as it is for the university researchers. So I think there are sort of multiple ways to interpret this. One could be these people are less competitive, but they're still competitive to some extent, maybe on 20% of projects that they're going to publish. You could also just think that maybe there is some sort of residual omitted variables bias that we can't account for, and that's showing up here, and that's what's driving the downward slope, in which case I would say then you should think that the difference in these two slopes is really how much of the effect we should attribute to the competition. And I'm sort of happy with either interpretation. I think I can't sort of take a super strong stand on which is the right one. Okay. So then finally, and this is actually new, the last thing we do.
Sorry, just taking a step back, so it sounds like it's just the consortia that should do the.
Sorry, say it again.
It seems like we should just give all the work to the consortia instead of the universities to do it faster.
They do it faster and at higher quality. Yeah, and it's interesting actually. You read, so the structural genomics initiative got shut down at some point because it became clear they were not going to successfully solve every protein structure. But then you can read accounts of whether it's a success or a failure, and you can tell these two groups of people don't like each other. They feel like they're fighting over the same pool of resources. So these people will say, you know, they worked on like proteins nobody cares about, it's a waste of time. These people will say, we developed all these ways of solving proteins better and faster, and that was a huge win. And so, yeah, I think especially over time, they gained a lot of expertise about very good at this. I think.
Yeah. So the question I have is whether these teams are working on different proteins at the same time, and maybe they're delaying the position just because then the information that they make available with the position might actually help other, teams who are working on some other complementary proteins for which that information is useful. So then because I'm more competitive, if I'm working in a university, I delay the position even after publication, whatever, as much as you have 1 year period, correct, for collection. While if I'm working this consortia, I'm not too worried about that competition. So I will, and that's an additional reason maybe why they do this consortia, because they speed up the process because they complement information. Also other complementary products.
The university recruitment is a little complicated. I understand so I think you're saying like on the one hand, they're gonna, after they finish this project, they're gonna work on something else very related, so they wanna just hide it. But on the other hand, they could get spooked. So that's gonna push them to not sit on it too long. So I think the scoop fear dominates and most
Correct.
people think that was.
No, but if I understand correctly, they put, the question is, the collection is the first, once you crystallize, correct? Understand?
Yeah.
The deposition when you make available, it becomes publicly available.
No, so there's collection.
Yeah.
Then you upload it to the protein data bank, that's deposition, but it goes into the secure holding tank, nobody can see it.
Yeah.
And then only when the paper is published, then everything is made public, including the deposition data and the collection date.
But then for this guy, the consortia, they publish the paper, the content.
No, so they'll deposit and release, the dates are all exactly the same.
That's why it makes sense.
But we were looking at the we were not looking at the release date, we were looking at the deposit versus collection. So that should sort of, I think, be not contaminated by that, yeah. Yeah.
So what's the added value of the paper compared to the depositing of the molecule structure?
I mean, it's the only way you can get citations. So people don't,
I mean, scientific.
scientific.
But from the.
I think it's just about, so, I mean, in large part, I think it's just about communicating your results. But then also often the papers will say, given that we found the protein has this shape, we now have new insight into how it functions, this is what we think it does. So, there's some more, but yeah, that's a good question. It's not totally obvious, it's a ton of value add.
I'm just wondering whether like over time there's been increased improvements in software that might sort of attenuate this effect. Like if we're thinking about deposits that happened before 2000, maybe some groups have certain access to software. Now whether we see this like impact on model quality actually is much smaller because everyone has really good access to software.
It's a good question. So our data ostensibly goes back to the 1970s, but because of the exponential growth in deposits, the vast majority of our sample is actually quite recent. So I think, if we were to throw out everything before the year 2010, we would still have well over half of our data. So I think we should check.
No, I just thought it was interesting because it's like, I guess, in a lot of fields of science, we now have many open source tools that are not to. Maybe these can help to sort of stop these problems.
Yeah. And it's nice in the data, they tell you the software programs that they used. So you can actually look and see when people are adopting new software programs and the implications on quality, for example, which is pretty cool.
So what is the standard? What are the standard errors for? Are they similar for both types of researchers? The error bars around these?
I'd have to. Everything, I don't know off the top of my head, just the standard errors for the different coefficients.
Yeah.
Like the slope and the interacting slope. Everything is significant at the 1% level, I know that, but I don't have the regression tables in the slides, I can take a look. But
So I was just wondering if there's way more variance.
yeah, no, it's a good question, yeah. Okay. Then this I'm happy to talk about because it's a little bit new. The last thing that we did to sort of try to test whether the model we have in mind is the right mechanism is that we actually ran a survey experiment. So we reached out to almost 3,000 structural biologists who are depositing in the protein data bank. That's where we got their email addresses. We got a response from about 350 of them. And in the survey experiment, we asked 2 questions. The blue and red is just showing you what we randomized. So we say, consider the following scenario. You are working on a project and you have generated some preliminary results. Based on the research question and your results, you expect that it will publish. And then we either say, a high impact journal, general interest, or a medium impact field journal. Then we ask them, how likely is it that another research team is working on a very similar project? And they can answer anywhere between 0 and 100%. So if our model is right, the people who get randomized into the very high potential project should report that they think it's more likely someone else is working on the same thing. The next question we ask them, and sorry for the block of text, we say, consider a different scenario. And we cross-randomize these. We say, suppose you have generated some preliminary results for a project. Now we just try to directly manipulate their beliefs about how competitive it So we either say, you're fairly confident that nobody else is working on a very similar project, less than a 10% chance. Or we say you're fairly confident that somebody else is working on a very similar project, greater than 90% chance. And then we say, answer the following, sorry, that should not say 3, should say 2. Answering the following 2 questions with this scenario in mind. So then the next thing we just say is, how long would it take you to complete the project and submit to a journal? And they can choose a slider of how many months. And then we ask them a series of questions that are meant to capture quality. We ask them a series of things. We say, would you do this thing? And they can say yes, no, maybe, or not applicable. To avoid these slides being really crowded, I just picked one, which I think is the most important one. We ask them prior to publication, would you rerun or replicate the key experiment? And they can say yes, maybe, no, or not applicable. But we also ask things like, would you run additional supporting experiments? Would you check your code? Would you check any analytical work in the paper? So we ask them actually, I think, 6 different things, but I'll just focus on this one because I think this one's the most important. And this is, you can see, it's just it's meant to just be a very direct test of the model that we have in mind. So this is what the results look like. So this is from the question where we ask them, how likely is it, do you think that you have a competitor? And sorry, this is a typo. This should say low potential and this should say high potential. And so you can see that people report that it's much more likely that they think they're going to have a competitor if we prime them to think their project is very high potential. So it's about a 20 percentage point difference. The p-value it got truncated because I asked state it around. It's not literally 0, but it's 0.00 something. And then we can do the same thing for maturation. Now, sorry, so now what we're experimentally varying how competitive they think the project is. So when we tell people that it's not so competitive, they say that they're going to spend longer before they submit it to a journal than if we tell them that it's very competitive. And then here is one of our quality measures. This is, we ask them, how likely is it that you replicate the main experiment? If they say no, it's a 0. If they say maybe, it's a 1. If they say yes, it's a 2. So it's a 0 to 2 scale. It looks like if we tell them it's not very competitive, they are slightly more likely to report that they're going to replicate the main experiment. This effect, the p-value is 0.12. For most of the other measures we use, actually, the p-value is much smaller, but I think this is the most important measure. So this is the one I wanted to report. So this again just sort of seems like it's further confirmation that the mechanisms we have in mind are operating. And it was also nice to run this survey because it gave us the opportunity to think about external validity. So what we did was not only did we survey structural biologists, we surveyed researchers in 9 other fields and asked the same set of questions. And that then what we can do is just plot the coefficients. So basically just the differences between these bars, we can plot the coefficients for all of our fields. So in gray, we have the structural biology. These are people pulled from the protein data bank. And this is a different group of structural biologists that we tried to assemble from Microsoft Academic Graph, just to make it a little bit more comparable to the other researchers. And so this is the first thing I showed you, which is this is the coefficient on high potential in a regression where how likely it is that you have a competitor. So this is how much people respond in terms of, do they think they have a competitor, or we tell them their project's important. And you can see it's consistent across fields, but this effect is bigger in structural biology. Structural biologists seem to think it's more, they respond more to being told their project is important. Then I can show you the results for our regressions where we manipulate competition and see the effect on maturation and on quality. And here, structural biology is a little bit less of an outlier. It looks similar to other fields. They have a slightly bigger maturation effect, but their quality effect is sort of very much in line with the fields, especially in line with other, if you pick out sort of the more life sciencey fields, it looks very similar. So this provides sort of additional evidence that this is a sort of a pervasive force, especially the response to, especially the quality response to competition. Structural biology, it seems like, may have more of this effect where the most important projects are done poorly, because there seems to be this very tight link in structural biology between importance and competition. That's sort of definitely stronger here. But this general phenomenon that people, when they perceive that they're under competition, are going to do lower quality work, and despite these measures, seems to be somewhat consistent across fields, which was nice to be able to do this because I think a lot of people, just don't know how to generalize from structural biology. Okay. So that's sort of the end of the empirical results. Now I just want to touch on a couple welfare related items. I'm gonna do like some sort of super tidy, clean analysis and tell you exactly what to think, but just touch on a couple different issues. So the first thing I think that's important to just think about is, should we care about this at all? Does quality matter for how useful one of these structures is? And I think the short answer is that it just depends on what you're trying to do with the protein structure. So if you're just trying to get a sense of how this protein structure sort of works inside of a cell, actually a pretty crude map can be very useful. So it's not that these low quality structures are totally useless, but there are certain use cases where a really high quality structure is needed. And in particular, the one case where it seems to matter the most is for something called structure-based drug design, which is when you're trying to design a drug that's going to target a particular protein, which means that you need a drug that's going to fit into a very specific crevice on the protein. So if you have a really good map of what that space is, that can help you think about what should the shape of the drug molecule be. And in fact, this is sort of so important that there's basically like these thresholds in the literature where they say like, if you don't have 2.5 resolution or better, or R3 at 0.25 or better, which these cutoffs are stringent, like a lot of the structures in our sample don't meet them, you're not gonna be able to design a drug around this protein. Yeah.
Are there follow-up papers just for the purpose of higher quality?
Yes, I'll get to that in a couple of slides. That's exactly right. So the first thing we can do is just try to show that it seems like these thresholds do matter. And so drugs work by targeting and binding to a protein. And so we use data from this resource called Drug Bank, which tells us for every drug, what protein does that drug target? And then if that protein is in the protein data bank, it gives us the links to link back to the protein data bank. That lets us make figures that look like this. So let's just start on the left-hand side. Here I have this raw refinement resolution measure. What's a little bit confusing is I've gone back to the raw measure. Lower here corresponds to better quality. So I have the quality on the x-axis, and then I have the number of drugs targeting the structure on the y-axis. And this is a bin scatter. But you can see that as you move to the left and you exceed this quality threshold, it does look like there are more drugs targeting those high quality proteins. This is very cross-sectional. I would say it's just suggestive, but it's in line with this sort of very precise advice given by the structural biology community. And this is just doing it using the R3 cutoff. So it seems like the quality effects we're talking about here matter for certain use cases of these proteins and in particular drug development. Now, the next thing I want to talk about is, will follow-on work fix the problem? And maybe so much so that we just shouldn't care about this at all. So in a standard quality ladder model, researchers could just costlessly build on rushed lower quality structures. And if that were the case, we might actually like that people push quick and dirty work out very fast. But what I want to argue is that in our setting, to make a marginal quality improvement is very expensive. It requires resyncing many of the same costs that the original team had to sync. The protein data bank actually estimates that it costs about $100,000 to redo one of these structures. So I think like one way to sort of think about this is if people remember like the AstraZeneca clinical trial for the COVID-19 vaccine, they released their results, but it came out that they'd made a bunch of mistakes in actually running the clinical trial. They'd been under a lot of time pressure, and they'd given some people half doses instead of full doses. At that point, the study was pretty low quality. We didn't know what to make of the results. And if you wanted to improve the quality of that study, it would not be a matter of just recruiting a couple more people. You really have to go back to the beginning and start again, because the work you've done up to this point has sort of been contaminated and it's not useful. And structural biology, I think, has an element of this. If you rush, or especially early in the process, and then did a lot of work on top of that, the only way to really do better is to go back and start again. So that means that if this is sort of your model of science, it would be more efficient for the first team to slow down a little bit, do a better job in the beginning, than to have a second team come in and pay a lot of the same costs all over again. So it would be more efficient to do it well the first time. Yeah.
Is this also true if it's the same team?
It depends on where they cut the corners, but if they cut the corners early, like they just took the first crystal that they could get and it wasn't very good, then yes, it would be true for them, because they're going to be pretty constrained by the quality of their crystal. And then they tried to build a model with this crummy data, but really they just are going to need to go back and regenerate data. So we did look who does the redeposits. Sometimes it's this, who does the sort of redoing of these structures. It is often the same team, and they are collecting new data when they do that. It's about 50% of the time.
And the crystal is destroyed during the process of scanning.
That is true, although they could probably save extra crystals, but just the crystals themselves are not sort of well ordered enough to generate good data. So they would need to try to change the conditions under which they're crystallizing these proteins to get a potentially better quality crystal. And so if this is the model of science that you have in mind, it leads to sort of two potential sources of welfare loss. One is just the quality we don't get. And then the other is the cost of resolving structures to gain the residual quality. And so to try to get at what these costs are, we say, what if these researchers behaved like structural genomics researchers? We sort of say that's like these structural genomics researchers in some sense are sort of like the social planner. They solve structures without regard for whether they win or lose the race. That's how the social planner wishes the university researchers would behave. So why don't we use them as our sort of to compute counterfactuals? So that's what we do. So here I'm showing you the same thing I've showed you many times in blue, the negative relationship between potential and quality. In red, I'm showing you what the counterfactual quality would have been if these people behaved like the structural genomics researchers. So this triangle here is the quality that's missing, at least initially. But then what we can do is we can say, okay, let's not look at the first structure that gets deposited. Let's look at the best version of the structure that gets deposited. So if other people have come along and deposited the same structure in the protein data bank, let's grab the best version of that. So now I'm plotting that in blue with these counterfactual researchers in red. And what you see is that almost all of the missing quality gets recovered by people who come along and do the follow-up work. It could be the original researchers or it could be new people. So it seems like at the end of the day, we're not missing a lot of quality, although it does take time for this improvement to happen. So that's a loss we don't necessarily take into account. But even if you ignore that and you say we get all the quality back, we still estimate that we're paying somewhere between $2.2 and $5.5 billion. Just if you say that these structures cost $100,000 each to do, we're paying that much in structures that we really think their only purpose is sort of to clean up the original work that was shoddy. That's a big number. I mean, that's I think more than we spent, for example, on the Human Genome Project. So just in the sort of context of science funding.
So, but it didn't have any data on the structural genomics for people on the upper quantiles of the bench.
That's right, although it was not terrible. This is what it looks like. So I would say we're not doing like wild amounts of extrapolation. It's about 3 data points. It's about 15% of the sample. We're sort of extrapolating beyond what we have. Yeah, so it's not ideal, but I think there's a pretty good range of common supports. I don't feel totally uncomfortable, but if you look at the goal of this exercise is to sort of benchmark us on orders of magnitude. I would not say it's meant for anything more than that. So,
but also apparently the academics also didn't have the lower quantiles.
Yeah. So there's for sure. I mean,
could you restrict the sample for the SG people just to like the upper quantiles that they do have, and then do this counterfactual rather than the. So
I mean, one thing to note here, these are bin scatters, so it's not saying, of course, there's no data out here, it's just that it's sparser. And so this also is potentially sort of overstating in a way and extrapolation we're doing, but yeah. Yes.
I take a step back to like the bigger theory questions.
Yeah.
Because I guess yesterday you started out right by talking about how for basic research it's not really like incentivized the money, it's incentivized the credit. And I guess that kind of suggests doing like the analog of like an optimal tax problem here to think about what's the optimal way of allocating credit, where like winner takes all credits.
Yeah.
Seems inefficient for the reasons you discussed.
Yeah.
So I mean, not necessarily as a feasible practical thing, but there is a question of like, what's the optimal allocation of
And
credit?
actually, it's interesting, that was sort of the original way we framed the welfare analysis in this paper, is trying to think about how much should the winner get relative to the second place team. We moved away from that a little bit. I think in part, actually, I might say this just in the conclusion, I think part of the reason not to do that is just competition is doing so many different things at the same time. We're measuring just one. So we're measuring the effect on quality. But I think like the bigger thing actually it does is it prevents people from talking to each other and sharing ideas. And so that actually might slow down science, but without sort of thinking about all the relevant margins, any exercise in sort of optimizing, I feel like it's not like going to be intellectually honest because we're ignoring all these other like really.
I think even you could like avoid quantifying things, right? Just going through the conceptual channels.
Yeah, so that was how we sort of set things up before. We said there's like the social planners problem, and then there's the individual scientist problem, which involves, and part of that problem is about the relative share of credit you get for being first or second and doing sort of comparative statics around that. But at the end of the day, we were like, it was a little bit hard for us to we couldn't make definitive statements, like it should be more equal or it should be more unequal. So it felt very unsatisfying. So we moved instead towards just trying to say, what is the distortion induced by people sort of not behaving in this pro-social way? But it doesn't really, we don't know how to change that. So it's the nice thing, the credit share you could imagine is a policy lever. Just saying, I wish scientists behaved as a social planner would like is not a policy lever. So I agree that that's like in some ways it's a little bit unsatisfying. If you just take this given that they're going to compete, what should we do? And this paper doesn't really offer a super nice answer. The one thing.
But you could change journal publication guidelines.
Yes, and that's happening actually. Some journals now are putting out statements where they say, here at this journal, we commit, if you get scooped and you send us your manuscript within 6 months of the sort of winning paper, we commit that we will treat it as if it was novel. And their rationale is exactly like, we think that the competition is becoming too intense, it's leading to perverse incentives. So this was actually like sort of how we motivated the paper once upon a time, and we moved in a different direction. Not clear if it's the right thing, but something we thought a lot about. The last thing I'll say that's also sort of an interesting policy implication. If you think back to our model's like a little bit particular, and you might think it's like sort of too specific in the sense that all the uncertainty is in the first phase. When you're trying to invest and start the project. And then once you started the project, or once you have your crystal, at that point, quality is just a deterministic function of time, how long you spend on it. And you may think like, why'd you model it that way? That's not so nice. And we might have said, yeah, we kind of agree. But actually, we learned this really interesting historical fact about the field that makes a lot of sense in the context of the way we set up our model. So it used to be the case that in the 1970s, the field was very small, people all knew each other, and maybe 2 people were working on trying to solve the same protein, and they're trying to crystallize it. But back in the 1970s, once you generated a crystal, you would actually publish a short paper saying, this is how I crystallized hemoglobin, and here's how I did it. Why would you do that? Why would you tilt your hand? Because at that time, there was a norm where if someone else had successfully crystallized the protein, everyone else, that was their cue to walk away from this problem. And then they could work on building the model without any threat of competition, which is actually exactly the solution, the policy solution we want to our model, because you like multiple people working on it when there's uncertainty in terms of who's going to succeed. Once that uncertainty is resolved, there's no benefit to having multiple people, and actually there's a cost because it leads to this racing, which we don't like. So in the very particular context setup of the model we have, this is like actually the optimal solution. And so the fact that it sort of arose endogenously, I think maybe suggests that the way we're choosing to model this is not a terrible representation of the way this field works. I love this quote. There was a tradition that if someone had produced crystals of something, they were usually left alone to solve the problem.
It sounds like animals fighting to be alpha in a group or something, where
yeah,
all these evolutionary mechanisms of competition that doesn't really get result in a fight.
Yeah, exactly. Yeah, it's like they knew that the sort of race to finish was costly, and so they wanted to avoid that. Now, sort of my understanding is of what happened is as the field became very large and people don't know each other, it became much harder to enforce the sort of gentleman's gentlewoman's agreement. The norm fell apart. people now no longer publish papers about how they solve the crystal because that's only just showing your opponent how to do it, and they're not going to respect this as their cue to back off. So this doesn't exist anymore, but I thought it's sort of a very interesting historical fact and sort of ties in very nicely to the model that we have. Yeah.
Sorry, I'm a little confused. The quality of the model is sort of some function of the quality of the protein crystal, right?
Yes, that's.
So wouldn't this still
So it's not-
encourage a race?
It's not perfect. So I would say the quality of the structure depends in part on the quality of the crystal, but then holding the crystal constant, spending more time doing this thing called refinement further helps quality. So it's not, the distinction is not as crisp as I'm trying to make it sound, but there's sort of I think there's an element of it here.
But it sounds like you could just split the credit. I mean, at least if data storage is not an issue, right? You get credit for crystallizing, you get credit for then solving.
Yeah, and actually, like one of the people who won the Nobel Prize for the ribosome, really her contribution was the crystallization part. So you could imagine that people would then specialize also in different parts of the process, but I don't think that that's actually what happened. So just looking at the time, I think I'm out, so let me just wrap up here. So as I was sort of saying to Max, I think calibrating the optimal priority rewards, the optimal split of credit, how competitive the field ought to be is a little bit beyond the scope of this project. Just because competition, I think it permeates science in so many ways that are not considered in this project, which I think are actually just really important and interesting areas for future research. You know, the stories I've heard about the secretiveness that scientists, things like, oh, our lab has too many windows, so now we label our test tubes with internal lab code, so if someone looks in the windows, they don't know what's in the test tubes. Or a friend of mine told me some story about she wanted to run an experiment using a protein that the lab next door purified. So she said to her advisor, I'm going to go ask that for some of it. And he said to her, you can't do that because they know what we do. And if you're asking for this protein, they'll immediately deduce the experiment you want to run and they'll just run it before you. So she said she spent 9 months purifying this protein to run an experiment that failed on day 1. And I think that this type of behavior is just so costly and it's really a byproduct of this competition that we have. I think it likely impacts who enters certain fields and who is deterred. And I hope that this can just bring up interesting questions of alternative models of organizing science, in particular, you know, some of these more collaborative structures like the protein structure and the Human Genome Project, and think about, you know, what are the costs that these systems have? When are they going to work well? When is competition going to work well? But just, you know, how can we think about trying to organize science in a way that creates good incentives and lets us be more productive? So I'll stop there. Thank you.